So here in video 2 we have the hairless guinea pig, who we already know has 2 lowercase alleles, 2 recessive alleles, or he wouldn't be hairless. If he had a capital H in either of these positions, he would have hair because that capital H is dominant and bossy. Alright, so let's see what happens next. Genotype for the hairless guinea pig. Well, we already figured that out. This guinea pig is purebred, meaning that both of his alleles are the same, and we know that both of them are lowercase because he has the recessive allele. So we're going to mark this right here, okay? Is he heterozygous, different, or homozygous, meaning same? Well, those 2 lowercase h's are the same. He is homozygous. All right, and what did that poor guinea pig who needs a sweater look like? Is he hairy or hairless? Hopefully everybody got this far. Doing pretty well. Round 2. All right, fill in the blanks for the situational sections below. And the allele is a specific form of a gene. So you have a hair allele and a hairless allele for the same gene. Let's move on. We have a Punnett square here with the parents already marked. We take this allele and it goes this way, and this allele goes this direction, meaning that for this capital H and this capital H, this possible baby is going to have 2 dominant alleles. This goes again the same direction. We have a dominant H from mom and a lowercase h from dad, just for the sake of it being neat and not messy. We're always going to put the lowercase after the dominant allele if there's a dominant. Here again we have the dominant allele coming this direction, the lowercase or recessive allele here. The lowercase also comes down here, but what happened here? We've got a lowercase allele coming over here. So out of the 4 possible genetic combinations, doesn't mean if you have 4 babies, one has to be homozygous dominant, one has to be homozygous recessive. It means these are the possible babies. Okay? If I cross this parent with these alleles, with this parent with these alleles, these are the 4 possible babies that could happen. It's a roll of the dice. It's a possibility, but nothing outside of this square could happen, okay, from these parents. Number 7, in the Punnett square, how many alleles does a baby guinea pig get from the mom? It gets 1. Each of these is 1 baby. It got 1 from mom. It got 1 from dad. Dad sent 1, mom sent 1. That's how you get to 1 plus 1. Imagine that. Number 9. Now, let's explain. If a baby girl guinea pig looks almost identical to its mother, does this mean that it inherited more alleles from its mother? We know that each baby gets 1 from mom and 1 from dad. So if it looks like mom, mom must have had mom passed on more dominant alleles than dad did. We don't look like dad because dad gave us those recessive genes, okay? Mom passed the dominant gene, so we look like her.
You?
Yes, you do.
Just making sure.
All right. Now, here we get to the word problems. Yay, everybody's favorite part of math, right? Well, it might be your favorite part of biology, too. Mysterious Fred, a guinea pig test cross. Now, the Amoeba Sisters told you the story about the teacher from Texas that loves hairless guinea pigs. It's one of the Amoeba Sisters, okay? We know that the dominant allele, capital H, codes for having hair, and lowercase h codes for the trait of being hairless. Okay, so now this teacher has a hairless guinea pig named Genevieve. So Genevieve is hairless. She's double recessive, homozygous recessive. But here comes Fred, mysterious Fred. We need to know Fred's genotype. Genevieve is hairless. She has the genotype lowercase h, lowercase h. Fred, the hairy guinea pig, has two options. We don't know what his parents looked like, so we can't figure that out. But we know he has hair, so he has at least one uppercase allele. Do we know what the other one is? No, and so we're going to do a test cross, which is like a Punnett square in real life, where they have a litter of babies and we look at the children to determine what the parent's genotype is. So Fred has one dominant allele because he's hairy. He might have another dominant allele, or he might have a recessive allele. We'll see what he passes on to his children. So we're going to mark these options. Is this looking familiar? Is this what you marked? Now, here's our test cross. If Fred was genotype homozygous dominant, homo meaning same, and mated with Genevieve, who is homozygous recessive, what would create, that would create which Punnett square? And the creator of our lovely worksheet here has a mistake. We don't have the correct option here, so you couldn't do this online, and that's fine. I will not take points off for this. I'm going to look at your explanations. Punnett square homozygous dominant by homozygous recessive, or homozygous or heterozygous dominant with homozygous recessive. Which one of these is it? It's this one. We have the correct answer here, but not in the box. If you didn't catch that, that's okay. Number 13. If Fred was genotype heterozygous, hetero meaning different, so two different alleles, and mated with Genevieve, who is still hairless and has two lowercase alleles, that would create which Punnett square? What do you think? We got this guy, so it's this one. The heterozygous dad with the homozygous mom. And here's what babies could result. We could have two heterozygous and two homozygous recessive. Those are the possible babies from this test cross. And last of all, explain in our own words how the offspring from that test cross would help determine Fred's genotype. We can guess Dad's genotype by looking at the babies. but only if what? If the genotype of the mother is known. If we don't know either of the parents' genotypes, this gets to be a lot more complicated process. And so you wouldn't test it this way because you wouldn't have enough information. Now, what is the weakness of using a test cross to determine Fred's genotype? Well, a Punnett square only shows you the possible babies or the possible offspring. In real life, every time you roll the dice, it's a new chance. So you might get, I'm going to refer back to our Punnett square here. With Mysterious Fred. If I roll the dice for baby number 1 and it lands here, and I roll the dice for baby number 2 and it lands here, and I roll the dice for baby number 3 and it lands here, I'm not going to figure out Fred's genotype because I'm not going to see these other options. So because each new baby is a new opportunity for probability, for what's probably going to happen, you may not get all of the possible babies, and so you might make a wrong guess about his genotype. So in real life, you might not get, or you don't always get, all of the options. Okay, and that's the answers and the explanation for that first assignment. I hope that was helpful. If you are going to complete or correct and turn that in, go ahead and do that now. If you have already turned it in, you should have the option to go back and make corrections. Thanks for watching.